So let's start the afternoon session, which will be devoted to the mainly fractal-like stuff. And the first speaker will be Andrey Gromov from Brown University. We'll talk about the multiple gauge theories in practice. So,
I want to urge you then. I'm sure everyone is aware that.
I'm not sure, but I'm supposed to be moderated, so.
Did you clap to people that they should stop eating? I guess I'll just start talking slowly. I would think Chauvin invited him, but he's not here. Okay, so I was asked to give a little bit of an introduction to fractons and symmetric tensor gauge theories and all that. Maybe not the best person to do it, but I'll do my best. So first maybe 30-40 minutes with introduction, therefore. If you don't know much about the topic, that's this part of the talk is for you. So fracton is just now a generic word that refers to quasi-particles that cannot move freely. If you create a quasi-particle, sometimes a quasi-particle can move anywhere it wants, but sometimes it can't. So I would like to explain in the first few minutes how this can possibly happen. How can a quasi-particle not be able to move? So sometimes they can move, but they can only move on smaller, lower dimensional submanifolds. So this is an example where they can move like this, but not like that. Sometimes even more bizarre thing happens. Quasi-particles can only move together simultaneously, and when they move, their trajectory is a submanifold, but submanifold of a fractional dimension. This is a picture that if you keep repeating it will turn into Sierpinski triangle. This is also colored. So to understand why sometimes particles cannot move, let's just talk about something completely trivial and understand why other particles can move. So I learned this from the talk by Liang Fu. I'll just repeat what he said at some point a couple of years ago. So in E&M, if you just, not even in E&M, if you have a charged matter, every particle is charged, and one way to understand why a particle can move from left to right is to imagine that you have a particle and you use the charge conservation. So you pull out a vacuum, a neutral object, you don't violate any conservation law, and this object can take form of a dipole. You can pull out a vacuum anything you want as long as the total charge is 0. But let's pull a dipole. So if I take this dipole, I can move it to the left so that the negative charge denoted as blue annihilates the positive charge denoted as red. So if I move it to the left, I kill that charge, but my positive charge has halved. So I can, if I choose to do so, visualize any motion of the process as taking a dipole out of the vacuum. Dipole can be oriented any way we want, and moving the dipole to annihilate the charge, this way the charge will hold along the dipole moment. The dipole I pulled out of the vacuum. Okay. So, but sometimes it's possible to arrange a theory, a simple theory, where, can I have this? Can I have this? Thanks. Never calls on. Sometimes I can arrange a physical theory where I am not allowed to pull charged objects out of the vacuum, but I'm also not allowed to pull dipoles out of the vacuum. Okay, so just for the next couple of minutes, let's say I'm playing this game. I cannot pull dipoles. So suppose I can only pull out quadrupoles. Just what that happens. Okay, well then what happens? Let me try to use this quadrupole to hold the charge. Oh. Something happened, but it's not really clear what happened. I just annihilated the charge. Let me pull another quadrupole out of vacuum and apply it to these two charges. Well, if I do this one more time, this combination has come to the right. So if I can only pull out quadrupoles from the vacuum, what I can accomplish is that the charges cannot really move on their own, but the dipoles of those charges can. Notice also that in this example, dipole moves perpendicular to its dipole moment, cannot move along this dipole moment. So I can view this dipole as a composite particle, and within this set of rules of the game, this particle is extended in space, is characterized by some direction, dipole moment namely, and it can move perpendicular to its dipole moment, but cannot move along this dipole moment. Now, suppose I get just a tiny bit more creative and try to make this particle turn. So it cannot move along its dipole moment, but maybe it can turn. So I'll play the same game. I make a quadrupole out of vacuum, and I'll move it to annihilate this charge, and again something has happened. But now you can guess that this dipole can be moved down by placing more quadrupoles out of vacuum. So I can keep doing this, and I managed to take the green particle, and I managed to make it turn 90 degrees, and now it's a different particle characterized by a different dipole moment in the perpendicular direction, but I also have left something behind. I have left behind this dipole. And this dipole, as you can see, it's under 45 degrees to this and to that. So it still seems like I'm playing some random game. I could have chosen any charge configuration I wanted. And this is what trying to understand fractals is really about, at least in my view. Can we use some language to specify what can be taken out of vacuum? So, in ordinary story that you're familiar with, I would just say that I have charge conservation, and because of this, only densities, charge distributions whose integrals are 0 can be pulled out of vacuum. So things that have total charge 0 can be pulled out of vacuum. Well, now that we understand that some more exotic rules of the game are possible, what I can do is I can say that only the charge distributions of certain type can be pulled out of vacuum. But now there is a question of how to characterize the charge distribution. Well, I can specify rho of x, but then I'm in this infinite space of functions. I don't really know how to nicely determine which classes of rho I want to be able to pull out of vacuum and which classes I don't want to be able to pull out of vacuum. So instead of characterizing charge distribution in terms of functions, I can switch to another description, and I can characterize the charge distribution in terms of its moments. Okay? And now if charge distribution is continuous, then I need infinite number of moments to specify it. However, in the examples that we discussed, the charge distribution was discrete. So it just has finite support, so I only need finite number of moments. Okay? So this is how I'm going to mathematically phrase the rules of the game. I'm going to say that things that have a certain fixed moments can be pulled out from the vacuum. In ordinary charge conservation, you fix 0th moment, just integral. If you want to conserve dipole moment, you fix the first moment, etc. I guess I said. So if you have finite support, I need just finite number of moments to completely characterize the charge distribution. Dipole conservation means that first and the 0th moment are conserved. The example that we just discussed in pictures has 3 things that are conserved. Charge, first moment, and trace of the second moment. But now there is a little bit of a problem. Or maybe not a problem, but a feature. So each time we talk about moments or charge distributions, they usually kind of have finite extent in space, right? And because they have finite extent, you should always compare this finite extent maybe to a UV scale or lattice scale or something. So there is a question of how do I think even of pulling out a multiple moment out of vacuum. So one way I'm imagining it, I don't know of a better way, is I just imagine a charge configuration that satisfies the constraints that I have imposed. Let's say satisfies the 3 constraints that we just discussed. 0 charge, 0 dipole moment, 0 trace of the second moment. And to visualize how it is annihilated into the vacuum, I'm going to just say that I'm going to keep scaling it, and I can scale it completely to 0 if my scaling parameter is going to 0. So I cannot, see, because I have so many constraints, I cannot just take this charge to, I cannot merge these charges under arbitrary trajectories. I can only merge them coherently. And one way to do this is by doing scaling. Incidentally, multiple moments, they have very well-defined nice transformation laws under scaling, transformed by n power, if it's nth moment. On the lattice, the situation is really funny, because on the lattice, I can imagine playing the same game, but now I have a lattice. And having a lattice means that points in between the lattice vertices actually don't really exist. I only have lattice vertices. So there, to annihilate these moments, I still can do scale transformations, but it's only the discrete scale transformations that are allowed. And these discrete scale transformations are determined by the lattice size. So for example, if I take this configuration, if I scale it by, so that this 1,1 charge becomes here at position 2,2, then this is a good scaling transformation is allowed. But if I scale it so it moves here, that's not allowed. So there is a discrete scale symmetry acting on the multiple configurations, or change configurations defined in the lattice. So I am just talking about constraints. Of course, in the physical theory, we would rather take these constraints and not to impose them by hand because we like this particular set of constraints. Ideally, we would like to have a physical theory with a set of symmetries, and the symmetries would lead to the constraints, just like U1 symmetry leads to charge conservation. Unfortunately, or again, maybe fortunately, in the cases that you perhaps more used to, the conserved quantities are always scalars. There is a theorem or something that says that in Lorentz invariant theory that should be the case. But clearly dipole is not a scalar, it's a vector, right? So if I'm saying dipole is conserved, then I'm talking about the conserved quantity which is not a scalar. And that has profound impact on dynamics of these theories. One thing that immediately implies that such theories cannot be Lorentz invariant, but perhaps more importantly, it implies a lot of very other subtle features which I'll discuss throughout the talk. So higher moments, of course, have the same issue. They're tensors, they're not scalars. So whatever symmetry leads to conservation of these objects is going to be, again, not your usual type of symmetry. It's not going to be a space-time symmetry because charges are involved, and it's not going to be a internal symmetry because the charges are not scalars, they're vectors. So I will come back to the symmetry maybe in about 20-25 minutes. But before talking about the symmetry, maybe it's worth discussing some theory that we already know really, really well, and that has been discovered a long time ago, but happens to fall into this class of very bizarre things that I'm talking about. We have studied physics for 2,000 years. Maybe we have already discovered some of these theories before. We just didn't really realize that they can be phrased this way. Of course, the answer is yes. Studied everything. And the theory in question that behaves like this is elasticity. Elasticity is a theory that describes a continuous medium. The main degree of freedom in the elasticity theory is the displacement vector. So if you have some small but macroscopic element of elastic body and you apply deformation, this element will move from one position to another. This displacement is characterized by this vector ui of x. You can write an action for zero temperature elasticity. It just consists of a time derivative term and spatial derivatives. And the spatial derivatives are, they're made of this hue, and it's a symmetrized gradient. So uij is just given by this formula. Okay? If you write equations of motion, you will just discover equations of motion for two Phonon degrees of freedom for elastic lattice. You can derive this, you probably didn't use some undergraduate class before. This theory has a symmetry. The symmetry is kind of trivial. You can take my elastic body and just move it, and dynamics is the same. So I can take all of these hues and I can move them by a constant. And the symmetry implies a conservation law. And in elasticity, this conservation law is called second Newton's law. It says that time derivative of momentum equals to force. Okay? So it seems that so far this has nothing to do with anything, except that we have a bizarre symmetry where the parameter is a vector. But it's a vector, it's not space-time vector. It's not space-time translations. It's not relativistic theory. So, turns out that we can rephrase this theory in different variables. So what we can do is we can introduce a new set of variables where momentum conservation, this equation, is automatically enforced. So how to do that? Well, we take this stress momentum tensor. I'm emphasizing this point because it's not T mu that you're used to, it's Ti mu. It doesn't have energy part in it, it's just momentum and stress. We take the stress momentum tensor and write it as a exterior derivative of a vector valued one form. So it's this AI rho is a one form, but each component is a vector. Okay, and representing a stress momentum tensor this way implies that I can modify this AI mu by a gradient of a vector, and stress momentum doesn't change. So description of this elasticity in terms of AI rho has a gauge redundancy. Every A's that are different by each other, differ from each other by a gradient of a vector, are physically equivalent. They lead to the same momentum and stress. Okay. Now, it so happens that when you write stress tensor this way, and if you take just spatial part, Tij, stress tensor ends up being not symmetric. And you can a little bit massage the theory to make sure that it's symmetric. You can hard enforce the symmetry constraint. Okay? It's not rocket science. You just demand that Tij equals Tji and see what kind of constraints you get onto Aij by doing this. If you impose this constraint, you find that it's possible to introduce a slightly smaller set of gauge transformations in fields. You can introduce just a symmetric tensor Aij that transforms now by two derivatives, di dj of alpha. And you can introduce a scalar potential phi that transforms by alpha dot. Now the way you go from here to here is you essentially end up saying that the symmetry of stress tensor implies that Ai alpha I is gradient of a scalar function. That's what symmetry of stress tensor implies. So after symmetry of stress tensor is imposed, we can write Lagrangian for elasticity, but in terms of these dual variables, vector potentials. And well, what you have to write is Maxwell, but Maxwell is made of electric and magnetic fields, which are gauge invariant combinations of this Aij. Okay, so it's electric field, but it's not the usual electric field that you're used to. It's electric field with two indices, and you can think of it as roughly speaking Aij dot. And magnetic field in two dimensions in Maxwell theory would be pseudoscalar, but here it's a vector, and it's roughly speaking curl of Aij.
So what does this gauge transformation correspond to in like real crystal? Is it?
It's just redundancy of description in terms of this double variables. Gauge transformation is not it's not the symmetry. It's just we introduce some variables, but certain combinations of this certain values of these variables happen to be identified, cannot be physically distinguished. So this gauge transformation just makes sure that we don't overcome.
But I thought like this description of the elasticity in terms of this gauge field is not really physical in the sense that some of these gauge transformations really correspond to different arrangement of atoms. Like you can physically distinguish.
If atoms are indistinguishable, I doubt.
Okay.
Yeah, I'm not sure what you mean. Maybe there's some science I'm not aware of, but I'm not aware of this. I would say that these are just identifying different physically equivalent configurations of A. So this gauge transformation also leads to a constraint, and constraint in terms of this gauge transformation, say this form, this electric field is divergence equals to rho I, and in terms of this symmetric variables we have introduced, the Gauss law takes this form. It's electric field, and the electric field sits under two derivatives. Di, dj, eij equals to the charge density. Charge density is defined as something that's conjugate to the scalar potential, whereas There's also charge current, and charge current is defined as something is contributed to the tensor vector potential. So it turns out that this Gauss law, although looks very harmless, that was very important, simple observation made by Michael, leads to quite interesting properties for the dynamics of the theory. So, first of all, the total charge, according to this Gauss law, should be zero, or rather, integration of this formula just tells us that spontaneously charge cannot appear out of nowhere. If I take some small ball and I call it M in space, charge can only appear in this ball by flowing through the boundary. It cannot appear out of vacuum. But what's more interesting is that dipole moment also satisfies a similar constraint. If I integrate x times rho and use the Gauss law, I find the dipole moment in the small ball M also is zero, or in other words, can only float through the boundary of the ball, cannot appear spontaneously out of nowhere. Now, if I go further and I calculate this for this quadrupole moment, I find this quadrupole moment can spontaneously appear out of nowhere, and if it appears out of nowhere, there will be EIJ electric field. So if I add energetics, and I say that creating electric field out of nowhere costs energy, then appearance of quadrupole out of nowhere will be unlikely, but it will not be kinematically impossible. Whereas appearance of dipole moment out of nowhere with this Gauss law is kinematically impossible. So it seems that because of this constraint, the theory that these gauge fields couple to has to conserve charge and dipole moment. Okay? And usually in this type of dualities, this type of transformations, the matter that dual gauge end up coupling to is describing the defects. Okay? So the matter with this bizarre conservation laws is just defect matter for the crystal lattice. Okay? So rho and J describe defects. So let's just talk about defects. Defects have been understood also a long time ago. In two dimensions, there are two types of defects, disclinations and dislocations. And let me first talk about dislocations. So dislocation is the following crystal defect. If you take the crystalline lattice, you remove a line of atoms, and you end up with a missing line of atoms. This is a defect. The way you detect this defect is you go around this, let's say this point. So if I go around this point, let me move twice left, twice down, twice right, twice up. I made a circle, but I ended up translated from my initial point. This translation is a charge of this defect. It's called Berger's vector. And for this particular picture, just let me repeat it, go like this, I end up here. So I went from here to here, the Berger's vector points this way. Okay? Well, this Berger's vector is a charge, it's a vector, and it turns out that dislocation cannot arbitrarily move through the crystal. So the way it works is like this. Dislocation, since we are in two dimensions, can either move on the square lattice, can either move up, down, or it can move left, right. Okay? So if it moves left, right, along this Berger's vector, then all I need to do to move dislocation from here to here is to rearrange how atoms are connected. And I can just freely move it like this, all the way. There are no constraints on this movement, except energetics, but we are only talking about kinematics. Now, if I try to move dislocation up or down, then I have to change something in the lattice itself. So if I move, for example, this dislocation up, then to move it all the way to the next lattice side, I have to erase the lattice side. And usually in crystals, lattice sides do not spontaneously disappear into the vacuum, nor they appear out of vacuum. Okay? So if the lattice sides are not prohibited, are not allowed to disappear or appear for no apparent reason, then this motion is prohibited. Okay? Dislocation cannot climb. In real materials and real crystal, what happens is that you are at finite temperature, and sometimes, because of the thermal fluctuation, an atom can just break out of where it sits and flow through the sample, and because of this, dislocation can climb, but the probability is exponentially small. So movement of dislocation like this is kind of easy, and moving dislocation like this is hard. But at zero temperature, we can just impose hard kinematic constraint. So dislocation cannot move perpendicular to this Burgers vector, can only move along this Burgers vector. In elasticity, this is called glide constraint. It's been known for 100 years by now. There's another type of defects. So as you may have guessed, dislocations are the dipoles as we have discussed. They can move along some directions, but they cannot move along other directions. The dipole that defines the dislocation happens to be perpendicular to the Burgers vector. Because dislocation can move along this Burgers vector, but if I do dislocation of dipole of something, then the dipole will be perpendicular to the Burgers vector. Okay. Now, if dislocations are dipoles, what are the dipoles of? Well, the dipoles of another type of defect. And this type of defect is called disclination. Now, it's much more difficult to draw, so I have to steal the picture. And disclination can be visualized in terms of something called Volterra construction. So imagine you have perfectly square lattice, and what you do is you take one of the links and cut your lattice along this link, and either add a chunk of material or you remove a chunk of material. So here, for example, there is an added chunk of material. So the way you notice that there is a disclination as you start looking at vertices. You see here, every vertex is 4-valent, whatever the right word is. 4 links emanate from a vertex, 4, 4, and here 5. So there is disclination here, there's a defect. Here is still 4, here is still 4, here is still 4, so there's disclination that is localized here. Disclinations cannot move at all. Now, this is a bit difficult to visualize, but also known for quite a while that if you try to move dislocation, if you try to move disclination, it's going to leave a trace of dislocations behind. If you are to define a current for dislocations, this one, and for disclinations, this one, then the current of dislocations does not satisfy a continuity equation. Instead of it satisfies continuity equation, where on the right-hand side there is a current of disclinations. So what this equation tells you is that if you have disclinations and they are moving and their current is theta j, then conservation law for dislocations is violated. So dislocations appear out of nowhere. Okay. However, dislocations cannot appear out of nowhere, because to introduce even a single dislocation, you have to remove at least one lattice side. But lattice sides cannot be spontaneously removed or cannot spontaneously appear. So dislocations cannot climb and dislocations cannot spontaneously appear, but because they cannot spontaneously appear, disclinations cannot move. So these disclinations, they cannot move at all. And again, it's not going to be obvious, but you can play yourself with the pictures and you will see that it's more or less true. Every dislocation can always be visualized as a dipole of two disclinations. Now, if you are, if you prefer elastic language, it's quite difficult to visualize because you have to draw two disclinations and then try to see whether you get a Burgers vector when you go around, and you will. Another way of thinking about this is to realize that this is a really prehistoric way of talking about curvature and torsion. Dislocations are defects in translational symmetry. You end up translated when you go around the circle, so you have torsion, whereas disclinations have defects in rotational symmetry. You end up rotated when you go around disclination. And if you kind of play a little bit with Riemannian geometry with torsion, you see that there is a relation that you can come up with between torsion and curvature. Curvature, roughly speaking, equals the derivative of torsion. I find it quite amusing that in ordinary gravity, the degree of freedom that's preferred is described by curvature. Whereas in elasticity, the low energy degrees of freedom are those dipoles, which are described by torsion. It's a contrast. So, quick historic comment to make sure I make as many arguments as I possibly can. These symmetric tensor gauge theories are not new. They have been first discovered probably before this, but this is the earliest paper I know, by Kleinert, who was interested in precisely what we have just discussed with you, dual theory for elasticity, And he introduced the symmetric tensor gauge fields in 3 dimensions, though. He wrote them exactly using the formulas we just discussed. So this is a quite known subject. These papers go pretty well forgotten, but they exist. So all of this was understood a long time ago. Now, what was not understood a long time ago is that the symmetric tensor gauge theories are not just useful if you're describing something's dual to elasticity, but instead you can let elasticity go and just think about gauge theories of symmetric tensors, or maybe tensors that have symmetric and anti-symmetric components, or any combinations thereof. So one example of such theory that, as far as I know, does not have elastic dual is vector charge theory in 3 dimensions. So in 3 dimensions, you have Gauss law, you have electric field that's symmetric tensor, you have a vector potential, which is a symmetric tensor, and you have a charge, which is a vector charge density. And you have a magnetic field, electric field, and you can write Maxwell theory out of it. But what's interesting, and I'm using, is that the transformation property of this symmetric tensor vector potential coincides exactly with the transformation property of a spatial tensor under diffeomorphism. If the diffeomorphism is given by the vector field alpha j, and this transformation property is written in flat space. So this is a spatial gauge symmetry, spatial quantum gauge symmetry for linearized gravity. So in this theory, there is a property that charges are, all vectors. They're characterized by the charge, which is a vector, and there is a constraint that prohibits them to move along the charge direction. They can only move perpendicular to the direction of this vector. So they can move in 2 dimensions. It's for every vector in 3 dimensions. There are 2 directions. Now, because the charges are vectors, there is another quite interesting property. So, because charges are vectors, then you might ask a question: what happens with those charges if I am not in a flat space but in a curved space? I can take a vector, which is charged, which is supposed to be conserved, and I can try to parallel transport it around the curved surface. Well, if the charge is a scalar, that's fine. But if the charge is a vector, as I'm parallel transporting it, it will keep rotating. So, even stating that a vector quantity on the curved space is conserved has to be done with lots of care, because vector quantity will not be conserved even in a simple operation of moving it around. It will rotate if there is curvature. This can be, so this is the property of matter, right? That vector charge cannot be conserved. But this property of matter manifests itself in a bizarre property of this gauge theory. So in this tensor gauge theories, you can also make an attempt to just force them on the curved space. Suppose you want to calculate stress tensor. Right? Well, Maxwell theory, I just put it on curved space and I can calculate stress tensor, no problems. With those theories, there's a problem. The problem stems from the fact that the gauge parameter, so Tj alpha here, is a vector. So alpha itself is a scalar, the derivative of alpha is a vector. So if I am to write a covariant transformation law, I have to make this derivative covariant in curved space, as Christoffels, to make sure that this is the rank tensor. And the magnetic field has the same issue. I need to write a covariant derivative. I cannot just keep an ordinary derivative because AKI is a tensor. And because of this, if I calculate the transformation of magnetic field under the gauge transformation, I end up with a commutator of covariant derivatives. In flat space, commutator of derivatives is 0, so magnetic field is gauge invariant. But in curved space, commutator of covariant derivatives is not 0, it's proportional to the curvature. So magnetic field is not gauge invariant, it's proportional to the curvature. So the theory experiences a breakdown of just gauge symmetry at the classical level if you have curved space, which means that in the areas where the space is curved, there are more degrees of freedom. Because gauge symmetry just tells you what degree of freedom. Now, it seems that relationship between the curved space and those theories is a bit more complicated. It's not just the second you introduce curvature, nothing can, the theory loses its symmetry. Turns out that sometimes, if you are placing theory on a particular manifold, it still retains its gauge symmetry. But if you try to place it on generic curved manifold, it will lose the gauge symmetry. So the coolest example of this that I know is was discussed in this paper. It's a three-dimensional traceless scalar charge theory. So traceless means that there's a hard constraint electric field trace is 0, and scalar charge means that the Gauss law is di dj eij equals rho. So such theory, second I specify Gauss law, I specify the gauge transformations, so I know everything about the theory. Such theory cannot be placed in an arbitrary curved space, but it can be placed on an Einstein manifold, spatially. Now, this is shown by brute force calculation, and we don't really understand the whole kind of relationship between the multitude of tensor gauge theories and the multitude of what kind of curved spaces they can be placed on. It's a whole research problem. It's not being pursued. Finally, this is a gauge theory, so this is a gauge field. And one thing that we can do in 2 dimensions is to try to write something like CHERN-SIMONS theory. I'm sure Yizhi will talk about it more. I just wanted to make a quick comment here first for you to know that this exists. You can write CHERN-SIMONS theories. But the CHERN-SIMONS theory, for the reasons I just discussed, is not exactly a topological theory. So what it has non-propagating degrees of freedom, so it is topological in that sense. However, it cannot be placed on curved space because the gauge symmetry breaks down. So it's not topological in the sense that the partition function does not depend on curvature or on metric. I cannot even define the partition function on curved space. Okay. So let's come back to discussion of symmetries. Or if there are any questions, that's maybe a good moment to ask them. So, as promised, we'll discuss symmetries. What kind of symmetry can lead to the conservation of dipole moment? It should be something terrible. It maybe not too terrible, but it is definitely bizarre. So let me get started with an example. Imagine I have a scalar, real scalar, and I write an action that's invariant under shifting the scalar by a constant. Then there will be a conserved charge. Conserved charge density. This conserved charge density will be conserved charge. The conserved charge can be written as integral of charge density, and in this particular theory, the charge density will be proportional to time derivative of this real scale. Integral over space, so that doesn't match. Now, if I want to force conservation of dipole moment, what I can do is I can demand that there is another symmetry, which is perhaps quite unusual. I'm going to demand that this real scalar theta is shifted by a linear polynomial in coordinates, and I'm going to consider an action for which this transformation is a symmetry. Meaning, I'm going to consider an action such that when I shift theta by a linear polynomial on x is invariant. Okay? Now, it turns out that it's not very difficult to construct such actions, and they were constructed really, really long time ago for some multicritical component purposes by Lipschitz. What you write is theta dot, that's the usual term, but instead of theta Laplace theta, you write d squared theta, d squared theta. If you put one extra derivative on theta, well, you ensure that shifting theta by linear polynomial is perfectly fine. Right? Because second derivative will always annihilate linear polynomial. So shifting theta by linear polynomial is a global symmetry of the section. If it's a global symmetry, we can ask the question, what does Newton theorem imply? Newton theorem implies that the charge is integral of x with rho, which is a dipole moment by its definition. I learned about this story from this paper, where I guess people who just wanted to study Lipschitz critical points. And to study Lipschitz critical points, we need to have a good reason why the more relevant term d theta is prohibited. And it can be prohibited by demanding this symmetry. It's not really important for my talk, but that's why these people studied this before the fractal story comes in. So what I'm going to do is I'm going to just gauge the symmetry and see what kind of gauge fields I get to get to symmetric tensor gauge theories. And well, there's maybe more than one way of gauging such symmetry. The way I'm going to do this, following Michael's ideas, I'm just going to say that theta is now an arbitrary function of space and time, and I'm going to introduce a gauge field into this section in such a way that transformation of the gauge field compensates transformation of theta by arbitrary function of space and time. Well, that's reasonably easy. What I'm going to do is I'm going to introduce covariant derivative where I take di dj theta and I subtract the aj. If you ever worked with a real scalar, that's essentially the same thing, but for real scalar it's dj theta minus vector potential. Here it's di dj theta minus tensor vector potential. Not much difference as far as formalism is concerned. Now with theta dot, you just have to introduce a scalar potential. So this theory is a theory where dipole moment is concerned. And we gauge the symmetry and we obtain symmetric tensor gauge theory. In this combined theory, the particles cannot move any way they want. They have to move in such a way that the dipole is concerned. But now it raises a different question. Well, we took the linear polynomial, but shifting theta by linear polynomial is a little bit bizarre because now my transformation, although I consider it global, depends on the point in space. And it's not even that's bizarre. What's really bizarre is that if I try to compute transformation, the commutator of translation with this transformation, I get non-zero. This should be more or less obvious because if I translate this transformation, I end up with lambda scalar product with a vector with which I can translate it. Okay. So the commutator of translation and this lambda and the shift by lambda is non-zero, it's a constant. So translation and this dipole transformation commute on ordinary gauge transformation, on just shifting theta by constant. Now, what this really means, if you try to look at the big picture, it means that this type of transformation extends the algebra of spatial symmetries. Usually, I would have algebra of spatial symmetries, Poincaré or Euclid or whatever have you, and I would have internal symmetries, and they don't talk to each other. Whereas here, they are really intertwined. I cannot make translation, so I cannot decouple these transformations from the space-time symmetry groups. They have no trivial computation relations. Which means gauging everything is really bizarre because you end up with very, very, very exotic types of gravity. Because if you want to gauge everything, you have to gauge translations and rotations as well. Now, this is just linear polynomials, right? But how would I conserve trace of the second moment? This example with quadrupoles that we discussed before. Well, the way I would do that, I would demand that there is another symmetry where I take mod x squared, so x1 squared plus x2 squared plus x3 squared, and I demand that shifting theta by that times the arbitrary number is also a symmetry. If I demand that, then the trace of the second moment is conserved. Again, just by applying Newton's theorem, you can see it. So this raises a question. How far we can go. We can take linear polynomials, quadratic polynomials, cubic polynomials, can get any polynomials. Well, the most general thing that I could think of is you just say that theta can be shifted by a linear combination of certain homogeneous polynomials. Right? So far we discussed polynomials in, let's say, in 3 dimensions, our polynomials for x1, which is degree 1, x2, x3, which is also degree 1, and x1 squared plus x2 squared plus x3 squared, which is degree 2. But I could take any homogeneous polynomial. So what I'm going to do is I'm going to say that theta is just linear combination with some coefficients and some homogeneous polynomials. the charges which are conserved due to the symmetry are linear combinations of various moments. Because this homogeneous polynomial needs not be a monomial. It can be like x1, x2 plus 3, x2, x3. This will lead to conservation law of q1, 2 plus q plus 2, q2, 3. Okay? So this would be the conserved charges. Now, if I pick them at random, it will turn out that I will have to give up some spatial symmetries. So let's discuss this. I cannot just take any polynomials without thinking. There are constraints that come from spatial rotations and translations. That's which polynomials I can pick. So one constraint comes from the fact that if I make a translation, okay, if I commute the symmetry that corresponds to polynomial PIA with the translation, then the commutator is equal to just this difference, where translation is done in the direction R. Okay? This difference is a polynomial 1 degree lower. Okay? So the constraint that comes from the set of polynomials that I have chosen is that the commutator with the translation has to be a linear combination of the polynomials of 1 lower degree. If I happen to forget to choose one of those polynomials, then I would end up not being able to include translation in direction R into the symmetry algebra. Okay? The same holds true for rotations, but for rotations, polynomial remains the same degree. If I make a rotation, then polynomial doesn't change degree, but just the coefficients transform.
For the translation, you are relating polynomial of a certain degree to
1 degree
lower degree.
Yeah, so this is, I sense a lot of notations. So IA is an index for polynomial of degree A. Here I have A minus 1, which is polynomial of degree 1 lower. Yes. Now, it's
How do you define polynomial symmetry with rotation? Because when you try to choose the coordinate x, actually you kind of choose the rectangular Euclidean Cartesian coordinates, right?
Yeah, so the way I define it is I just take x and replace it by xi times rij. Okay? And polynomial will have three possibilities. It will either become itself. For example, when polynomial equals delta ij times xi times xj, delta is invariant tensor, so it will become itself. Or polynomials will form some representation. They will turn into themselves under some discrete symmetry, discretization symmetry. Or you will end up with some polynomial which is not included, which means that this rotational symmetry in this particular direction has to be discarded. We will have an example of this, but I'll probably run out of time before we get it.
You consider discrete or continuous
Well,
rotation?
I consider it in detail continuous, and there are also some words about this. Discrete are harder because there are more possibilities. Now, all of this formalism corresponds to something that you'll actually learn really, really earlier in studying physics. So when you read Jackson, I guess, or I don't know, people nowadays read for electrodynamics, you find a formula that tells you how dipole and quadrupole, etc. moments transform under translation. Okay, so if you have a dipole moment, which is integral of x with rho, you make a translation, it goes into itself, plus vector by which you translate it times the total charge. Right? It's very, very easy to derive, very easy to understand the fact. Now, if you do it for the quadrupole, you get a little bit more complicated transformation laws, but the point is it's always expressed in terms of lower moments. So quadrupole is expressed in terms of charge and in terms of dipole, and R is where we translate. Now, usually, the conclusion is reached that the moments are well defined only when all lower moments are zero. Okay? Or maybe well defined is too strong of a word, but moment n is independent of choice of origin, if and only if all lower moments are zero. Okay? But it turns out that you can make a little bit more of a compromise, and this is this extra freedom for which this abstract formalism of polynomials is allowing for. So imagine, let me just explain it in an example, because it's the easiest to understand in this example. Imagine I have a system where dipole moment in x and y direction in this plane is zero, and is fixed to be zero, constrained by conservation law. But in z direction, I can actually have any dipole moment I want. Well, then, turns out that x, xy, and yy components of the quadrupole moment still are invariant under all translations. Well, why is this? Well, it's because this, if you write as a vector, has components 0, 0, z. Whereas, if I restrict this to be xy, I can only have r to be x or y. So this is always 0. And if my total charge is 0, this is also 0. So if I shift in any direction, I will always end up with the quadrupole moment in xy plane not changed. It will always be the same. It does not depend on the origin. So what I can do is I can constrain lower moments to be 0 in some directions, and then within those directions I can further constrain higher moments. That's what this algebra is about. That's why you can include only some polynomials of degree 1, some polynomials of degree 2, some polynomials of degree 3, etc. And this is why they are all so touchy about translations. How much time do I have?
20 minutes.
10 minutes. Oh, okay, so let's then, there's a lot of words, but let's look at some very, very simple example. So this is like high in two dimensions, but it's not topological. But I think it will illustrate everything I was talking about. So imagine a theory where dipole moment in 1 minus 1 direction and this linear combination of components of quadrupole moments are conserved. First of all, you can simultaneously force them to be conserved and keep translational symmetry in both directions. If your dipole moment only has form 1, 1, perpendicular to this, then this combination of components of quadrupole moment is independent of origin. As you can just check arithmetically. Now, this means that my elementary charge configurations that we discussed before, the ones that can be pulled out of vacuum, have this form. It's 1, 1, this is the minimum one. 1, 1, and minus 2 here. Okay? This has dipole moment in 1, 1 direction, and it's completely perpendicular to this, so it does not violate the conservation law of dipole moment in 1 minus 1 direction. Okay, now let's try to see what kind of motion of charges we can get with this set of constraints. Before that, so this is how you realize it with equations. You say that your symmetry has constant term, which is conservation of charge, term some constant times x minus y, which is a particular homogeneous polynomial of degree 1, corresponds to conservation of the dipole moments in 1 minus 1 direction. And the second polynomial, the reason it really works, it's degenerate with this one. It's degree 2, but it can be expressed as power of this one. So it's x minus y squared. If you calculate what it corresponds to, which component of quadrupole moment it corresponds to 1, 1, 2, 2, minus 2, you want to. So, and then it's easy to write the action. You have to introduce derivatives that are designed specifically to kill these polynomials. Okay? And now we have a little bit richer structure than in this Lifshitz case. It's because it is a particular linear polynomial, I can actually construct a term of degree 1 that kills this polynomial. This particular term is dx plus dy. It's clear that dx plus dy kills x minus y. So what I do to construct this invariant derivative operators, I just look for differential operators for which this polynomials lie in the kernel. And then I want to stop this at some gradient exponential. So I stop at degree 2. Or rather at degree 4, because two other polynomials are quadratic, but the terms in action are quartic in derivatives.
Sorry, is
Yes.
there a systematic way to find this derivatives?
I mean, it's linear algebra, you do it order by order, as long as it's finite, yes. So systematically, you know. Order by order, yeah. Okay. So we can gauge it. It is to some gauge theory. Gauge theory has 3 degrees of freedom, A1, A2, A3. It has a Gauss law like this. But if you're actually careful about what kind of dynamics these gauge fields can have, you end up with the fact that dynamics is always gapped.
잠깐만
Yeah. So there is some gauge theory that responds to it, but unfortunately it's not very interesting because no propagating degrees of freedom. But what's interesting is to figure out how, just let's draw pictures again, how these particles can be separated. What can I do? So now the only game I can play is with this charge configuration instead of this one. And it's important that it's -2 here. So I am now going to make an attempt to separate this particle from those two. So how can I do this? I start pulling from the vacuum these configurations and apply them here and here to annihilate as much of this charge as possible. Okay, so this is what happened. You can eliminate all of this, but then you have more charge here. You can do it one more time. You get even more charge. Well, total charge is conserved, total charge is 0, but each individual charge is huge. So if you can keep going, you find that along each one of these lines, charge grows exponentially with separation. Okay? So it's not fractal behavior, but it's something. Charge grows fast. Whereas in the quadrupole example, charge did not grow at all. You can just move the dipole. So you can view this as separating this charge from here. We are moving it up, but the more we move it forward, the higher charge we end up in the bottom. I think the general scheme is clear. We choose the polynomials, we write down effective theory, we gauge the symmetry that corresponds to those polynomials, we end up with gauge theory, and then we play with charge configurations. So can we leverage all of this to get to the Haah code? Before that. There is one more, okay, spoiler, yes we can. But what we can do instead is to play a little bit more with this two-dimensional theory. That's also really cool, although not topological. So what we can do is now we can try to condense charges. We can say that break charge conservation to mod 2, mod 3, mod 4, and see what happens. Well, because we break charge conservation, some of those charges that we obtained before would disappear. Right? If it's conserved mod 2, then for example, this, and that would be 0 because they're all 0 mod 2. So if charge is only conserved mod 2, then our fundamental degree of freedom is this guy. This is now 0 because that was -2. So what I can do is I can create a charge here, but then by applying this operator, I can hop it like this. So it can move, but it can only move along this line. It cannot move anywhere else. And it's not the dipole of anything. It's just how constraints work out. So there's some dimensional fractal particles, not dipole of anything. It can move along the 1 - 1 direction. What happens? So this is cool, but what's much cooler is to do break charge conservation to 3, to mod 3 rather than mod 2. Then I have two possible charge configurations: 1 1 1 and 2 2 2. So it should be clear, right? -2 is the same as 1, so this is 1, and -2 is -2, but 1 is the same as 2, so I also have this one. So I have two charge configurations. Okay. So now let's try to move. So we create one of these guys and we try to move this particle as far away as we can. Turns out that if you try to move it just by one lattice side, you will end up with some particles in the middle. There's no way to avoid it. However, if you want to move it by two lattice sides, you have to apply this yellow star operators here, here, and there, and green star operators here, here, and here, and everything in the middle just magically disappears. And you end up with charge here and here. Now imagine we have periodic boundary conditions, and this is identified with this. So we just created a non-local operator that pulled these three charges out of nowhere, moved them along this way, and annihilate it. That's not very exciting, but let's keep moving. So if we keep moving, we have to move now by, I think it's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. By 9 steps. Only when I move by 9 steps, they annihilate again. If I move by 8, I will have some crap in the middle. 7, crap in the middle. But by 9, again, everything magically disappears. But now there are also holes. There are parts in this picture where charges have never appeared. Okay? So if you keep going, I think you may already guess you will end up with colored Sierpinski triangle. So I did not want to draw a bigger one, so I stole this one from Benny Yoshida. And if you keep moving, next would be 27. 27 is a bit more difficult. You end up with 27 by 27, so 27 by 27 square, and there are bigger structures that are empty emerge. But in the end, the particle that was here, here, and there annihilate. Okay. So one way to think about it is that we have a non-local operator that creates particles out of nowhere, moves them around the torus and annihilates them. But when it moves them around the torus, it's not a line and it's not a surface, it's the thing in between. And I don't really remember what's the fractal dimension, but I think it's between 1 and 2. Okay, so generally this will work for 3K by 3K torus, but will not work for other tori. So there are these nice non-local operators, but only for certain sizes of the tori. For other sizes, you cannot really do anything.
Those
Okay,
empty spots are A by identity operator.
you can say this way. Occupy nothing.
Do you find that related to what the home you talk about in the movie?
I beg your pardon?
Do you find this related to what home you talk about in the movie? Probably not, but I'm just asking.
I don't know.
I don't.
Okay, so I guess in the last minute or two, how much time do you have?
Please finish shortly.
Sorry?
Yeah, please finish shortly. Yeah, there's no limit.
No time?
Yeah, so,
I can write up.
Okay.
yeah, right.
So you can play the same game to get to the Haah code. Now this is the polynomial. It's more or less obvious because you choose this one. You get, so these are the components of quadrupole moment that are conserved. These are the components of dipole moment that are conserved. Haah model works in such a way that there is translational invariance in all directions, but rotational invariance is not SO3, it's only SO2, and it's SO2 in this plane, 1 minus 1, 0, and 1, 1, 2. Now, it's not just translational symmetry and rotational symmetry you actually have also anisotropic while scaling, it's scale invariant, but it's not even Lifshitz. Time, space, and some other space coordinate all scale in different ways. So it's like Lifshitz. Moreover, if you actually very carefully look at this action, this Lagrangian, it has infinite symmetry in addition to all these symmetries. If you introduce x and y like this, in these directions, then I can shift theta by arbitrary smooth function of x plus iy and x minus iy. And this also is a symmetry of action. So it has immense amount of symmetry. Now to get to the Haah code, this is the last thing, I'm sorry, this is the last thing I'm going to say, is that we do the same thing, we figure out what are the charge configurations that satisfy all of these constraints. Turns out there are 3. This, and that. Then we break charge conservation to Z2. And I would end up maybe with 3 charge configurations, but it turns out that if charge is broken down to Z2, then the third one becomes not linearly independent with the first 2, so I get just 2 charge configurations. And these are the starting points for constructing the fractal operators in the Haah code. Though that's what these violated projectors look like in the dual lattice, where these are centers of original lattice or vertices of the dual lattice. So I guess I'll just stop here. Yes, do you want me to read conclusions? Fractals are interesting. Well, that's the conclusion.
Questions?
You have one slide on open questions, right?
I have a couple of questions that
Open
I
questions.
have not answered yet. Again, you probably don't want me to read all of this, but I think the point of the slide is to emphasize that how little we really know about this type of theories, and it would be cool if some of you could think about them as well.
So you have a bunch of these series of thetas.
Beg your pardon?
You have a lot of actions in terms of theta.
Yes.
So here theta is a real variable or
Yes,
it's a
real scalar.
real scalar. It's not a periodic.
I never really use this, this becomes important. Okay, this is good that you brought it up. So one glaring problem in all of this formalism, which is usually you're interested in this theories on torus. This is not a good symmetry on torus. This is a polynomial, not compatible with periodic boundary conditions. So actually, I have no idea how to do this on torus. It's an open problem, but bet you anything that it's just a question of creative technicality, not some fundamental abstraction.
So if we imagine theta is a periodic variable, like 2-pi periodic,
Oh.
do you know these series, are they stable as, you know, due to the compact?
I think you have discussed it on case-by-case basis, depending on dimension, depending on how high up the rank of the tensor is. I don't know if there is any bound. Also, some of these theories you can guess, maybe you can guess, they really are lower dimensional in IR, because if I go to really far IR, this is second derivatives and these are first derivatives. So it's really case-by-case basis. For this theory, I didn't think about it, so I cannot answer it today. But generally, we don't know the constraints. Don't understand the spectrum of these theories yet, what kind of theories you can get.
For the torus of a certain system size such that this polynomial symmetry can be defined.
So again?
With a torus with certain system size,
Yes.
the polynomial in this way, this symmetry.
This
can
is
be
exactly how it should work out. Yes. So when we know how to when we eventually figure out how to generalize this to the torus, then there will be this is where system size should appear. I don't know how to do this, but yeah. So torus size will be very, very important when we figure out how to generalize this to periodic boundary conditions. I guess this is how we would be able to derive from the field theory the degeneracy.
How do you compare to the Z2 Haskell?
I just compare the charge
Charge configurations.
Yeah. So after that, the second I have the charge configurations, I forget everything I said before. I start drawing pictures on the 3D torus and see how they feel. That's how he counts degeneracy. He uses some math, but that's how he counts. How many fractal operators generated by the species fit in the torus of given size.
Please go to your future directions or future questions, open questions, last one.
A couple of them have been solved, I think, by now.
What is this Coursera elasticity? Maybe you talked about it.
Oh yeah, this I did not talk about. This is the one that has been solved. So in ordinary elasticity, your Lagrangian, I have talked about this history. In ordinary elasticity, the Lagrangian depends on the symmetric derivative of the distortion tensor,
Right.
or on the displacement vector.
Right.
But what this means is that it doesn't depend on curl, right? What that means, it means that this order, the elasticity in this order, says that if I take elastic body, take a small ball on it, and rotate it, it costs 0 energy, which is total nonsense. It's not how real world works. So what that means is that we really should also add terms that depend on the curl. However, curl of u works as follows. If you make a global rotation of the elastic body, then curl of u transforms additively. So curl of u is just an angle, d epsilon ij di uj, it's an angle, so it transforms by adding a constant. Okay? Which means that angle should appear under derivative. Which means that the reason we write this dependence on curl, is a next order effect. Coursera elasticity is about incorporating the dependence on the curl. The degrees of freedom you end up with are phonons plus a, pardon for doing this, phonon for rotations. Sorry, Goldstone mode for rotations. Goldstone mode for rotations is not independent of translational ones, but it still can be defined, but it's gapped. So Coursera elasticity is a theory of two gapless ordinary phonons and dependence of the energy on rotations. There's 3 degrees of freedom, but this can be written, write a dual theory for that. It will have all these nice structures. This problem actually has been solved.
By whom is it?
Well, Leo spooked me a little bit on this one. There's a paper by Leo and Michael Hermele, although they don't use the word Coursera elasticity. And there is also a paper by me and Peppers where we do use the word Coursera elasticity, but the equation is actually the same.
Other questions?
with success. We will have a short break on the next talk with data talk.
Almost.
You just do the table.
Well, here there's generous enough.